So a continuous function f is shown above and defined on the closed interval -5 to 4. For how many values of b between -5 and 4 is the average rate of change of f on the interval b to 1 equal to 0? Give a reason for your answer. So, average rate of change, not instantaneous, okay? But how many? So we're looking for b to 1. I might mark that. Let's do a different color. Actually, that wasn't even a pen. There we go. So the second coordinate of our interval has to be 1. So we're looking for making the average rate 0 between those two. So what is another name for average rate? It's like 4 or 5 words. What's another specific name for the average rate of change? Yeah, good job. Say it loud.
Slope of a secant line.
Good job.
He's the coach now?
Nope, he's sitting in front.
Oh, in front of coach. Okay. Okay, so basically pick points for a b value where that makes the slope 0, right? What kind of line is a slope of 0? Horizontal. So I would maybe just do this, like just draw a line, horizontal line. And we see 2 points on our function that would give a 0 slope or a 0 average rate of change when we connect it to 1. Okay, does that help? Be specific. What don't you understand? Do you get what slope is?
Yes.
What is slope?
Just
Can you guys be quiet back there?
the average rate of change? Like how?
Be more specific. What is slope?
I just don't understand. It's 0. The slope is 0.
What is slope? The concept.
It rise over run.
Okay. So if we're rising 0 and running something, right?
Yeah.
That means it has to be horizontal because we're rising none. We're just staying straight. Okay? And we're saying average rate, which is a secant line. Just as a side note for everybody, where would the instantaneous rate of change be 0? There's only one place before 1. Nope. Instantaneous rate is the slope of the tangent line. So -3 right there, right? So that's different than the secant line. Secant line, we have to connect 2 points that are not 2 points instead of 1. Let's just say it that way. So, in other words, I want a 0 slope line that is this line right here, right? And so it's asking for points B, x coordinates, where that y value is 3. So it would be this one here for that point, and this one here for that point. Those are the x values, right, between -5 and 4, where the slope is 0.
Okay, wait, now I understand.
Okay, cool. Any other questions from that? That problem set? Cool. Do you guys hear my window?
Yes.
It is so annoying. It didn't used to do that. Maybe it's because you messed with it. Well, fix it.
I didn't touch it. What? This is not my fault. It's Mr. Beach's ghost.
Mr. B is still alive.
Thank you. You're the only one who's ever messed with my window recently.
So it's because it's always too hot or too cold for him.
Oh, I see. All right, let's look at the rest of 2.2. Quick review. Definition of a derivative. By the way, let's add in front of this f prime of x. It says it up there, but let's just add our notation in front of the definition of a derivative. So remember, we're taking that h value between 2 points and shrinking the points to where h goes to 0. and then evaluate our function slope between those 2 points as the points get on top of each other pretty much. Did anybody go home and study this pink box last night? Like I asked you to. Yeah, good job. Winner, the winner. So those are the kind of little things that I'm talking about. Like if you understand the background and you know what this means, then everything makes more sense, right? And I get time is an issue, but make time to understand what we're doing in here. Okay. This, I said this yesterday, but let's go ahead and make sure we're clear. We took the derivative of these functions. That was the process that we did. But it was using the definition instead of rules. Okay? I think Sonia asked about this. Was really, I think, a really important question to ask. Like, what are we actually doing there? So I'm just clarifying as a review that we took the derivative. What we ended up with was a function, it looks like a function, for the slope of the tangent lines plural, for the original function. Okay? That's what a derivative is. It's the slope of the tangent line. And so this would give us that slope for any point that we want on this parabola. And then over here, 1 over x squared, we ended up with negative 2 over x cubed. That would give us the slope for any point on that function. Good? That was kind of a fast review. So we reviewed then, we jumped into the tangent line stuff. Man, that assembly messed my voice up. I had to stand my freaking freshmen. They were misbehaving. Sorry. It was really not fun. Just messing with each other, like touching each other and whining and like just be here. It's not that hard. Yeah. We're going to use point slope. However, keep in mind that y1 is going to be f of whatever point we're looking at. So if I say you'll see it right down here. What's the tangent line to the graph at 5? F of 5 would be our y1 value, f of 5. Okay, and then f prime of 5, that's our slope. F prime, remember, is one of our notations for a derivative. So in the previous examples, we mentioned we'd have to go through that whole process to find the equation and then plug in 5 to get the slope at that point. Okay, that's a lot of work. These problems aren't going to have you work through that whole process. But it will later when we learn the rules. And then x, that just stays in our equation, and the a is just 5. So x, y, m. Everybody good on where those come from? Okay. So let's do number 5. You guys, hopefully you tried it last night and maybe you did good on it. Let's see. If we know h of 5 equals negative 2, that just gave us 2 important parts of our equation. Did you see that? What was it? This is x. This is f of x, or f of a. And let me keep consistent with that notation for this one. This is a, this is f of a. So we already know those 2 things. Okay, the derivative of h is given, so we don't have to go calculate that whole thing, that whole long process. What is this going to give us? The derivative of h, once we use it. That's the slope, right? And if we plug in 5, we'll have the slope at 5. Write an equation for the tangent line, etc., etc. So maybe start with this, y minus f of a, just because it gives you what you need to plug in. So it equals f prime of a times x minus a. So we know that the y is going to stay put. F of a, what is f of a? Negative 2. We need to calculate f prime of a, x, and then what is a? Is 5. We're evaluating, or we're writing the equation for the tangent line at 5. Okay, let's go find f prime of 5. I'm using the wrong letter. Let's do h prime of 5 for this one. So we just plug 5 in. 5 cubed minus 2 over 5. 5 cubed is 125. So our slope is 123 fifths. Is that okay to leave it like that? Totally. Yep. Don't do more work than you need to. Okay, so at that point, our slope, only at that point, by the way, our slope is 123 fifths. I suppose if it's curvy, it could hit that slope again, but for this, what we're saying is just at 5, 123 fifths. Questions on that? Did anybody do it last night? How did it go? Yeah, good, cool. Did anybody plug that into a graph? Okay. Do you see, what's the approximate value of 123 over 5, roughly?
Like roughly like 25, 24.6.
It's roughly 25. So if we went and put this on Desmos, that's a steep line, right? In most cases, that's a very steep window. So does anybody know what kind of function that is? Here, x cubed minus 2 over x. I'm just writing it bigger. It's a rational function of some sort, right? Good. Okay. Let's do, I want to get through this. I think we'll have time to come back, but we might come back and graph that, but let's just get through the rest of the lesson. All right, here's your first exposure to a derivative graph, okay? And we're going to see these a ton this year, but the biggest thing that I want you to keep in mind right now is that this is not f. It's not the function. What is it? Yeah, this is a graph of all the slopes of the function, right? So do you guys remember your increasing, like relating concavity and slope rate of change? Remember that? This kind of gets into that idea. So this is, again, in fact, it's probably worth saying derivative graph, not f. And it's pretty typical for them to just put f prime in this little thing like this one has, and you're like, you got to read close because you might think it's f, and it's actually not. So just look closely, but yes, this is a graph of all the slopes of the original function f. Okay?
What does the original function look like?
Well, so that is unit 8, I think. That's our last unit to be able to go backwards from an f. Maybe it's unit 7. But anyway, that process from going backwards from a derivative back up the chain is called integration, and it's cool. It's actually cooler than derivative stuff. We spend probably 2 months on that, and it's very cool. But you could kind of think, like let's just pick this area right here. This is the slope of f. So what is the slope doing right there? And that like from -2.5 or so to -1. The slope is increasing, right? It's positive, number one, because it's above the x-axis. It's positive, and it's getting bigger. So think of a graph where our slope is positive and getting bigger. Maybe something like that, right? Going backwards to the original. Okay. It's the very, let me get rid of this circle. It's the very biggest right here. That's the highest slope. And then what does it start doing? Now it starts decreasing, but it's still positive. So now it's going to maybe start doing that kind of thing, right? The original graph. And then we get down here. The slope is like 1.5, but still positive. And now it's starting to go back up again. So who knows what kind of graph it is. But what's true right here?
It's 0.
The slope is 0. So the original graph must have a horizontal part right there, right? Don't worry about this yet. We're going to get there. But since you asked, I wanted to show you. Yeah.
So is it like acceleration and velocity graphs in AP Physics?
Yep. Same exact thing. If I gave you the acceleration graph, could you come up with the position graph? It would suck, but you could. Okay? All right. Here's how this works. The graph of f prime, the derivative of f is shown at the right. If f of 2, not f prime, but f of 2 is 7, write the equation or write an equation of the tangent line to the graph at 2, 7. So, write your tangent line down. Honestly, when I do these, I do not write f of b and f of a. That is a conceptual thing. So I just do it with the regular formula because I know the difference. But maybe to start off, we can keep doing that. Either one, okay? You can substitute a and f of a for x1 and f and y1 if you want to. All right, y is going to stay. What is y1? That is f of a, right? What is it?
7.
It is 7. How do we know? Because it told us that f of 2 is 7. F of 2, not f prime. Okay, let's skip the slope for a second and get the rest of this filled out. X, what is x1?
2.
It's 2. That's where we're evaluating and writing the equation of a tangent line. So how do we get the slope? First of all, where do we need the slope?
7. 2.
Is it at 2 or 7?
2.
At 2, right? This is all about x. So we need the slope. Here's 2. We need the slope right there. Because this is the slope graph, I can just read the y value right off of it. And that's the slope at that point. Okay? So I'm going to draw a little arrow. That was not a good arrow. This is the slope of f at x equals 2. What if that was the graph of f? Well, now we have to go find the slope at 2, right? Which we would have to sketch in a tangent line, and that's not as accurate. So what is the slope at 2?
7. 3.
It's 3. There's the equation of our tangent line at the point 2,7. Any questions on that? Yes?
How are we going to know which one to use? Whether it's the y minus f3?
Oh, it's just preference. I don't care which one you use. I'm just showing you both. Whichever one makes more sense to you. Yep. Any other questions? There's not like an AP specific standard for that, so just whichever one you connect with better.
For AP grading, do we have to show the actual formula and then plug it in, or can we just plug it in?
So he's asking, do you have to write this first? I think that's what you're asking. No, you don't. I would be careful though, because you don't want to mess up. You know, it's pretty easy to write the formula just so you know where to stick stuff, but no, you don't have to. Yep. In fact, this whole problem, this is notes and teaching, but this whole problem would be sufficiently answered with just this. It gave enough information to not have to show any work at all and just write your answer. Once you get it, right? Yeah, cool. Any questions on section 2? the definition of a derivative and notation. Okay? Does anybody feel like you're getting a preference between prime and like Leibniz and Lagrange notation? The prime is Lagrange and the dy dx is... maybe you're not there yet, which is fine. I need to fix that slide so you can see it. Okay, a couple things on notation just to remind you. I know this got cut off. It's supposed to say 20 right there. If f prime of x is 2x minus 5, f prime of 6, that means just plug in 6, right? It's right there. So that's 7. That's the slope at some point, right, on this graph. Then it's incorrect to show it like this. F prime of x is not 6. F prime of 6 is something, okay? df or d dx f of 6, that's just the same thing. It's not 20. df dx of 6 is not 20. So we're not showing it that way. Here's the okay ways to do it. If you're going to show it plugged into Leibniz notation, so d dx f of x, that's how you show the left part of this. And then you draw a vertical line and show where you evaluated the slope, which was at 6. Okay? So with Leibniz notation, either one of these is okay. Or any of the three, I should say. Show the derivative notation, vertical line, where did you evaluate, and then equals whatever number it is. Okay? So let's practice that just to illustrate. If we go back to this one, go there with me. If we did Leibniz notation, it would be dh dx evaluated at x equals 5 equals 123 over 5. Okay? Our function in this case was h. dh dx that's the Leibniz notation for the slope, or the derivative at that point. We evaluated it at 5, and we got, this is work over there, we got 123 over 5. Okay? We already did the Lagrange notation here, so we don't really need to show that also. Up here, if we wanted to evaluate, let's say df dx at 2 for this one. So we want to know the slope at 2. What would it be? Just 1. We're just plugging in 1, or plugging in 2, excuse me. Whoa. Okay. So that's just some notation specifically with Leibniz. All right, look at the problems. Seriously, just zoom out. I think it's probably going to be good to try one of those big, long processes at least once. Okay? So which function do you want to do that on? Don't pick the easiest one. 3? All right, let's do 3. So do 3. Let's look at number 5 real quick, because we didn't really have one of those. We kind of did, but let's just do number 5 together as a quick example. So C is the number of championships. Actually, before we do that, read the directions. We're using the information to identify the meaning of the two equations in the context, right, in full sentences. So C is the number of championships Sully has won while coaching basketball. T is the number of years since 2002 for the function C of t. So what does this mean? Okay, how about the next one, though? This is a really weird scenario for me, I think. Yeah.
The number of championships he wins increases by 0.4 each year.
Close. In when? Because we need to. He said it right, but we need the when of it. Is it each year?
5 years after.
In year 12.
In year
Yeah, because remember, this is instantaneous rate of change at one point. So in year 12, Sully is winning 0.4 championships per year.
That's pretty good.
It's a really weird context for that to me, but whatever. So why don't you circle number 6, just to give that the D prime. Do you want 2 of those?
Sure.
All right. You want to do gray hair or cartoons? You guys pick. I don't care which one you do. All right. Equations of tangent lines. I only have 14 done right there. Maybe I should turn that. Okay, let's do 13, and just the more I feel like the more we can practice with trig stuff. Do 13 and 14. Just don't look what I have written there for now. And yeah, do the test prep, the usual. Do you find the test prep helpful?
If I can understand.
They're sometimes kind of hard. So we still have about 15 minutes. Let me ask you. Yeah, we get out at 55, I think, right? No, we get out at 40. We have 2 minutes. Never mind. On Monday, you need a calculator, so make sure to bring that. If anybody's dealing with eligibility, parent, anger, like that, just come talk to me. Let's work something out, okay?
My mom is convicted only. You won't see me on Monday. I'll send Pedro with my calculator.